So next, let's talk about the duality between the primal and the dual problem. So here's the general primal problem where we aim to minimize fx subject to an inequality constraint that gx is bigger or equal to b. And first, let's define the Lagrangian of this problem, which is equal to fx minus lambda times the constraint. And you're going to find out the primal problem is essentially solving the following minimax problem, where the mean is respect to x and the max is respect to the Lagrangian multiplier lambda. And to see why they're equivalent, let's look at what is the inside the max over lambda. And the value, we should get a function of x. We have to discuss two cases. If gx is bigger than b, then the quantity inside the parenthesis is positive, and the minus lambda is going to be negative. So to maximize, we have to set lambda to be 0. So when gx is bigger or equal to b, and that max over lambda should just give us fx. Now when gx is less than b, then what's inside the parenthesis, gx minus b, is going to be negative. So minus lambda times a negative number is going to be positive. So when we maximize over lambda, we're going to make lambda as large as possible. Eventually, the value inside the bracket is going to be infinity. So if we're going to do our outside minimization over lambda with respect to this function, and you're going to find out with respect to the primal problem. So the Lagrangian function has two arguments, like x and lambda, and we just showed that the primal is basically solving a min-max problem. We can consider to switch the order of min and max, so we get max-min. And usually, who takes max first is the winner. So usually the min-max is bigger than max-min. But under some conditions, and the equality holds, and that's a condition convex optimization will satisfy. So instead of solving the primal, we can solve the dual problem, which basically the max-min problem. Now for the max-min problem, what's inside the bracket is basically just x, the Lagrangian of x and lambda. So when we when we minimize respect to x, the inside minimization, based on that, we can just take derivative of x and of the Lagrangian function, set it to 0. That will give us some equalities, and we can use those equalities to eliminate x. So we're going to find out this quantity usually is just going to be a function of lambda, and we maximize over lambda outside. So the primal going to give us a solution in terms of x, and the dual going to give us a solution in terms of lambda. And they are essentially solving the same problem, but those two solutions will be linked through the KKT conditions. Let's look at what are the primal and the dual problem for the max margin. We have our Lagrangian function, which is the primal objective function minus each of the lambda I times the corresponding constraint. And then, as I mentioned before, when we work with the dual problem, is the max-min, and the mean is respect to x. But we're first going to look at the derivative of L respect to x, set it to 0. As we mentioned before, this is going to give us those two equalities. And we can use equality 1 to replace beta. You're going to find you're going to find out this term and this summation are basically the difference is just going to give us minus half of beta norm square. So that corresponds to this term. Now use equation 2. We're going to find out this term won't appear because sum of the lambda yi is 0. But that still is going to be the constraint because the constraint is the derivative of the Lagrangian function with respect to x is 0. And we also have this constraint that lambda I should be bigger or equal to 0. So this is our dual problem. Why we want to work with the dual problem? If you compare the primal and the dual problem, they both are the objective function are quadratic and convex function. However, for the dual problem, the constraints are much easier to work with. As I explained in the appendix, for the dual problem, we actually can eliminate this constraint because we can add. So the idea is, just add this square into the original and this quadratic term, so we get something like this. Then when we try to minimize the left hand side, we will force to make this part to be 0. So this equality constraint is sort of implicitly incorporated into the optimization. So you're going to find out, if you work out the detail, you're going to find out eventually you can rewrite the dual problem just as a quadratic function of lambda. Lambda is a vector from 1 to n. And now we're going to minimize. So this term becomes this term. And now this quadratic term becomes this quadratic term. Here lambda is just an n by n matrix with ijth entry equal to this, and subject to just a simple boundary constraint. So this can be easily solved by using algorithm like coordinate descent algorithm. So we're going to initialize lambda 1 to lambda n, and then we just going to go through a loop updating each of the lambda I by fixing other elements of lambda. And then for each of the lambda I, if we fix all the other lambdas, it's just a quadratic function of lambda I with respect to this positive constraint. So the solution, the updating formula for lambda I, will be in closed form, and we can just loop over and until convergence. But it is but we should be aware that the computation cost for SVM is in terms of a sample size n, not the original dimension p, because we are solving the dual problem. Because the dual problem and the variables are lambda 1 to lambda n, in term and is in terms of the sample size n. Although the primal problem is in terms of the dimension p. So you could have a simple SVM, you could have a data set where the dimension p is only 2, but if you have a million data set, then the computation cost for SVM is still large. Another reason for working with the dual problem is that many lambda I is actually going to be 0. This is because remember, we have this KKT condition, and we know that lambda i's and the constraints cannot be non-zero simultaneously. So that means if the constraint is inactive, meaning what's inside the bracket is going to be strictly bigger than 0, then lambda I must be 0. Well, in this case, for example, we have 7 points, but for all those 5 points, the corresponding constraint will be inactive, because we're going to have strictly bigger than 0 for the green points and strictly less than -1 for the red points. And then that means their lambda I is going to be 0. So among the 7 points, there are only 2 points, which is this green point and this red point. Their lambda i's are the 2 lambda i's are non-zero. So in short, when we retrieve beta, the beta as a p-dimensional vector could be non-sparse, but the beta can be represented by owning a small, a summation over owning a small number of samples, where the samples, the lambda i's are non-zero. And those are the data points called the support vectors. In this case, there are only 2 support vectors. Another reason we were going to work with the dual problem is because this computation, the place it depends on the data, the yi, yj, and about the p-dimensional feature vector, all relevant is just their inner product. You're going to find that we're going to utilize this property and then use this so-called kernel trick to operate SVM in a higher dimensional feature space.